Hi, I'm Brian Kim. I'm the Director of Engineering for the Pressure Products Company. This is the second of three segments about specifying side windows properly. The first segment was on the various aspects of safety related to pressure and other mechanical parameters. In that segment, I stated that one should not overstate the mechanical damage risk. The payoff for not overstating any given risk is that a larger universe of design options remains for addressing other risk factors. In this segment, I want to discuss a much more common mode of failure, chemical corrosion. I mentioned in the previous segment that mechanical damage-induced failures are very rare. In my view, the biggest reason for this rarity of pressure-induced failures is that this mode of failure is easy for people to understand. If the contraption you want to put your side window on is pressurized, the side window itself must be able to take the pressure and more. That's obvious, so everyone explicitly calls for the right pressure, and that's also why safety margins are specified for pressures. Chemical corrosion failures are much more common than pressure-driven blowouts. In fact, I'll go so far as to say that chemical corrosion has ruined more sight glasses than all other failure modes combined. And the reason is that, unlike pressure, most people don't think about it before specifying a side window. And what exacerbates the issue is that window materials, plastic and glass, are both commonly considered to be corrosion resistant. But nothing is resistant to everything, so for any given application, it's very important to make sure that window is not reactive towards the process fluid. A secondary issue is that some of the most corrosive liquids are common household materials that don't seem to hurt anything. And finally, reactivity varies enormously with temperature. So, in this segment, I'll go through some of the chemistry topics that you will have to think through before specifying a side window. Now, the vast majority of pressure-bearing side windows use silicate glasses as the transparent medium, so I'm going to go discuss the silicate glasses. But you should remember that all of the issues we discuss here apply to plastic windows as well. Plastics are made through chemical manufacturing processes, and for any given transparent plastic, there is something that will attack it.
Believe it or not, the fluid that has destroyed more side glasses than any other liquid is water. Of course, that's very counterintuitive since you use glass water cups at home, but you may have noticed that old water glasses lose their luster and you can't ever get them to shine again like when they were new. This is the water corrosion of glass. The fact that water eats away at glass became really obvious at the beginning of the Industrial Revolution. Back then, steam engines were the only game in town, and they boiled water under pressure. And they use expansion pistons or turbines to convert thermal energy into mechanical energy. And for those, it was very important to make sure that the boiler had the right amount of liquid water. So these engines had sight glasses. And these sight glasses etched away right at the seals. And when those leak, and of course that leaked, and when the leaks couldn't be resealed because too much glass had been lost, the whole sight glass had to be replaced. So that was the beginning of our understanding of what is now known as the hydroxyl attack of silicate bonds. It takes water, the hydroxyl anions, and hydroxyl anion is this, the OH minus radicals, and which act as catalysts. Now in these situations, water supply is essentially unlimited, so the rate of corrosion depends on the concentration of hydroxyl anions. You can see one depiction of how water reacts with glass right here. Basically, the hydrogen atoms don't really care which oxygen atoms they're bonded to. So here, this hydrogen is switching its allegiance from this oxygen to that oxygen, and the net result is that you wind up breaking the silicon-oxygen-silicon bond, which is the backbone of any glass matrix, any silicate glass matrix. When this happens to enough molecules, some of the glass will actually dissolve into water. And what's not shown here, of course, is the multitude of specific mechanisms in which hydroxyls help this process along, but pretty much the result is this. Water cleaves the silicon and oxygen bond that make up the glass matrix. Okay? The big difference between what happens in your water glass and the steam gauge sight glass is the concentration of hydroxyl anions and their activity. If the hydroxyl anions are present in small quantities and remain calm, like in your water cup, the glass is fine for a long time. But even here, the surface will become corroded, as we mentioned already, and it'll lose its shine. If the hydroxides are present in large quantities and are aggressive, then the glass is eaten away in a matter of weeks. Now, that could happen because of higher temperature, presence of other chemical species, or, in particular, alkalines or hydroxides that have lots and lots of these hydroxyl anions in their dissociated state.
Let me show you a sample that's been eaten away. This is a borosilicate side window, and it's easy to tell that a huge amount of glass has been etched away. Now this piece started out as a stepped lens, so some glass around the edges had been machined away during manufacture. But obviously, a lot of glass had been lost. This piece of glass was in superheated water application, so the corrosive agent that ate away all of this glass was just pure water. And this happened in a matter of months, not years. This is not a small effect. So, how did water eat away all this glass?
So, I've explained that depending on conditions, glass can be okay in water for many years or corrode away in weeks. Let me elaborate on the factors that accelerate corrosion of glass. Temperature and stress. Pressure factors in as well. This kind of corrosion is a case of the classic Arrhenius behavior that governs most non-biological chemical reactions. This is the typical form of the reaction. The important part about this is that it's an exponential. Exponential right here. Okay. Now, even if you're not mathematically inclined, I'm sure you've come across the expression that something increases exponentially. The variables we care about are this E right here and this T. The T is the temperature, and this exponential captures the observed behavior of hydroxyl attack on glass in a quantitatively accurate manner, and how corrosion rate varies with stress and temperature. Namely, at room temperature, glass cup is good for decades with little loss of glass. Raise the temperature by just tens of degrees C, and you lose millimeters of the glass surface in weeks. That reality is described by this exponential form, okay, right here, and specifically this T being where it is. The other important part of this equation is this E. Glass corrosion reaction is catalyzed by stress. Those of you who work with old pickup trucks probably know that those trucks start rusting right where the frame is most stressed. The exact same thing happens here. The effect of imposed tensile stress is described with this E value, which is the typical way of incorporating catalytic activity into a reaction rate equation. This is the result of how water vapor causes stress cracks to grow. Note the scales. The scale here on the x-axis is a linear scale, whereas here you have a logarithmic scale, precisely because we have an exponential right here. So if you have a relatively small increase in the stress intensity factor, for example, from 0.5 to 0.6, you have reaction rate increases or crack velocity increases by a factor of 100. Okay? And if you looked at our previous video, you'll recall that the most stressed parts of a sight glass are at the sealing gasket seats. So that is where your corrosion is most aggressive, and that's really where the leaks occur. Pressure doesn't normally have a profound effect on condensed phase chemical reactions, but there is an important indirect connection here. If the higher pressure is being used in your process in order to hold water as a superheated liquid state, then high process pressures correlate with high chemical corrosiveness. Okay? High pressures lead to accelerated corrosion. Okay? This is why large mechanical pressure safety margins don't translate to improved safety in these failure scenarios. As I said in the previous video, you can make the glass hold more pressure by making it thicker. But if the high pressure is actually causing enhanced corrosion, then a large margin of safety in the pressure scale means nothing at all. A thick piece of glass will corrode away just as well as a thin piece of glass and start leaking just as quickly.
Okay. Looking at this again, I can point out where the seals were. This was sealed along the side walls. You can still tell that the side wall was vertical right around here, and this is where the seal was, right along here. You can also tell how the water ate away at the glass. Here at the center, where the stress is the lowest, only a small amount of glass was lost. Here, at the seat of the seals, a whole lot more glass was lost, and in fact, the loss of glass was severe enough to leave an easily identifiable ridge right along here. Okay? This is another one of our products. This is a fused glass piece which is mechanically stronger than other types of side windows. But the glass here is still the same borosilicate glass as in the previous piece. Being surrounded by stainless steel doesn't make the silicon and oxygen in the glass behave in any different way. In fact, in a chemical corrosion scenario, this type of glass, this type of side window would start losing glass much more quickly. Right along the periphery of glass, there is a region of static tensile stress, and the glass will suffer accelerated corrosion right along this periphery where that static tensile stress is. And you can tell that the surface of this glass has already been starting to corrode away. But when a part of the glass in this kind of a structure is weakened, the pre-imposed stresses will cause some glass to shear and chip away. And you will see that right along the glass metal boundary when it actually happens. Okay? But when the glass chips away, that exposes fresh glass to more corrosion, and that goes on and on. So altogether, this type of side glass will lose much more material in a chemical corrosion scenario more quickly than the cheap annealed kind, because the chemical weakening of the glass will lead to chipping and physical separation of glass. In this video, I've intentionally talked about water. You don't need some exotic, toxic process to experience failures. Everything I described about water applies to bases as well, like potassium hydroxide, which you use as a household drain declogger. Fortunately, these failures tend to be slowly developing leaks rather than dramatic explosions. If your process fluid is just water, then the leak is just a maintenance hassle. If your process is some toxic liquid, that's a whole different story, even if the leak is slow. Then you may have to call the EPA to tell them that one of your side windows has been leaking a toxic liquid into the ground for an unknown period of time, which is going to make for a pretty bad day. Now, some vendors don't pay nearly as much attention to this issue as they do towards pressure safety margins. If you obtain your side windows from us, our sales engineers should ask about these issues explicitly and in detail. But regardless of who your vendor is, make sure that you bring this issue into your side window specifications explicitly. This is a very important issue, and it's well understood among glass scientists. Unfortunately, this information is very poorly understood by everyone else, so we commissioned a scholarly literature survey. You can download that from our website at the address shown. That's it for this segment. Next time, we'll discuss temperature-related issues. I'm Brian Kim for Pressure Products Company. Thank you for watching.